durability. Yeah, about durability of the concrete and steel structures in the second session. So the moderator for today's webinar will be Dr. Jyri Chandra. So I hope we can have a good discussion as always. So please share your insight and question so we can have a good discussion later on. I give the time to Dr. Jyri Chandra. Pak Jyri, silakan.
Thank you, Professor Antoni. So good afternoon, ladies and gentlemen. So welcome back to our concrete precast webinar series. So this is the seventh series, and this is the last one. I hope all of you still are interested in listening to our great speaker. So today we have two distinguished speakers. So without further ado, I will introduce our first speaker. So our first speaker today is Mr. Jyri Nieminen. I'm sorry if I will pronounce wrongly. So Mr. Jyri Nieminen is a senior advisor at Sweco Structures, Finland. And when he got his Master of Science degree from Tampere University of Technology and his Master of Business Administration degree from Helsinki School of Economics. He has 38 years experience in energy efficient concrete buildings and their performance in both cold and hot climates. He is a member of FIP Commission 6, Sustainability of Structure with Precast Elements. The title for his presentation today will be Durability and Sustainability of Precast Building. So the time for presentation will be 45 minutes and then will be followed by 30 minutes question and answer sessions. So time is yours, Mr. Jyri.
Yep, thank you. So to start with this building on the front page of my presentation, this is a full precast building, and it's standing on top of the sea. So it's standing on piles that were driven into the bottom of the sea and built then with the precast components. The interesting thing is here that the car park, which is under the yard deck, that's totally underneath the sea level. So the risks for water going into the building is quite high. But then again, during the design phase, it was really looked at very carefully and found the ways and means how to make the waterproofing so tight that it will keep the sea outside the building anyways. So now I have a problem going. Oops. Okay, this you already saw. There's a little bit history here. The concrete construction started in Finland already in the 30s or 40s, but not as precast element structures. This is a picture from Christmas 1963, when an apartment building under construction fell down. The reason for this collapse was that the basement structures were side cast concrete, and it was a very, very cold winter. The temperature was below -20 degrees Celsius, and the concrete froze. There was a heating system for the concrete structures to keep it above zero, but it didn't help because the system also failed, or the person who was guarding the system was asleep. Anyways, it went down. I remember it well because I live in the city where this happened, and we went to see. It was a very impacting pile of wood after the collapse. And the building was supposed to look like the building in the right-hand side small picture. And they, of course, cleaned the site and built it again, but that was the accident that happened. This was another kind of an accident in 1984, but there was a landslide underneath the buildings, but the concrete buildings stand as they were, and there was no damage the structures, but it was not a very easy process to repair the damages for the ground. But the engineers found a ways and means how to do it, and the building is still there, and it looks like a very typical concrete building in early 1980s in Finland. In the 1960s, there's a huge urbanization going on in Finland, and the demand for new apartments was also very huge. And at that time, Finland started to develop these precast concrete structures, as shown in this picture, and also the connections between different structural elements. And later on, when these buildings were built in the 1960s, 1970s, we got the energy crisis, and then we also started to add insulation into the existing structures. And that happened for these buildings outside. So they just added new insulation on top of the old structure and made a new facade for the building. This is one of the cases, and you can see the problems here, the rebars and the elements. You can see that there's the protective coat was too small. There has to be at least 2.5 centimeters of concrete on top of the steel so that it doesn't corrode. But and the poor quality, in this case, it also can see on the facades because it was slowly coming down piece by piece. And then the city who owns these buildings, they decided to tear down the whole facade so that the inner slab of the sandwich panel is still there. And then they built a new facade with the building high elements, building a factory. And this is the problems are due to too thin exterior layer of concrete in the sandwich panel. And then it's obvious that this kind of buildings will have facade problems. It doesn't mean that there's nothing wrong with the structure so that they would collapse. No, but just that the water gets into the insulation layer, and that's never a good thing. So these pictures under, you can see that the element is 4-story high, and it's just lifted up to the facade and attached there. And these elements also include the new ventilation system, the ductwork. So every room in the building will have a mechanical ventilation, and also the heat recovery for the mechanical ventilation was included into this element system. And here is what it came from. The outcome of this is the same building with the new facades and new balconies. So every apartment in the building got a new balcony as well in the renovation. The main how do you say it? Well, it also improved the energy performance of the building. It was classified as class E, which is the lowest energy class in Finland. Before and after the renovation, it was class A, which means the level of a passive house. So the energy consumption for heating of the building, it dropped down tremendously. And this kind of renovation has been done quite often in Finland, actually. And if you look at the ground level wall, there's a graphic concrete giving some kind of an images over there. Actually, those are constellations described in the wall. And this is a little bit newer building. This is when the energy crisis hit Finland. Also started to think about low energy buildings or zero energy buildings and so on. And when I was working at VTT, we developed a concept for net zero energy apartment building, and that was built here. Maybe you can see that the windows here are quite small, but that was a requirement by the by the building owner. This is a house for the elderly. And the problem was that if it becomes very hot, the elderly people don't feel very well. And so the buildings, the windows are quite small. But this was also, you can see that on the right-hand side picture that there's a huge insulation layer in the precast concrete elements. There's a 40 centimeters of high quality insulation, which gives a really low U value for the balls, so the heat losses through the building envelope are minimized. And also the windows are very good. The U value for the windows is something like 0.6, I think, 0.5. At that time, very new system. And also all the windows have a shading for the midsummer sun. If you know that in Finland, during midsummer, the sun is up all the time. So you can get sunshine all through the day in the midsummer. There are some pictures from the construction site. This is a concrete panel. You can see that the concrete layer inside and outside is quite small compared to the level of insulation in the panel. The floors were typical hollow core slabs. And actually the whole building is built with very typical concrete systems that we have in Finland and have been using those for about 60 years now. There was the second building, the two buildings like the other one. The one was for elderly and the one was for the students. It's a student's home as well. And these were then monitored quite carefully, and so we could state that the original target was reached, the nearly zero, the net zero energy building. And it's also peculiar here that one of the buildings, they have a heating and cooling system.
Hello.
They have ground source heat and cooling.
Kamu di mana?
Rumah.
And they also have a lot of solar collectors on the roof and also solar electricity systems. And the systems, the ground source heat and the solar collectors produced too much of heat for the building, so they started to sell it to the neighboring buildings. So slowly they can cover up the investment into the systems by selling heat to the other buildings. This is also quite new project, very big one. It's also an elderly care center in Lahti, Finland. The idea here was that before this design started, the owner wanted to make a kind of a list of things that has to be fulfilled in the design and construction on the building side, so that the building will have a very good properties and it will be sustainable, low carbon and so on, but also that it fulfills the needs of the elderly who will be living here. And these two issues, they conflicted a little bit. Like this huge atrium they have, that, it's not very good idea to have that kind of an atrium in a building where in the summer sun is shining all the time, so it becomes very hot. But then again, you can cool this atrium and use the excess heat also for heating the hot water in summertime in the building. So there's also kind of a combination of building technologies and HVAC technologies that are considered in the same design, and that also helped that it really become a nearly zero energy building. I think it was the first big building having this kind of a status in Finland. And this was also a building where VTT was working at that time, make the concept design and all the simulations and calculations to verify the building and the properties. Now, the carbon neutrality in Finland is a hot topic, and some people want to have Finland carbon neutral by 2035, the whole country, but that is a little bit too ambitious goal for a country. But individual cities, like the city of Tampere, they look at the carbon neutrality by 2035. And these cities, they have a quite well targeted and created strategies how they are going to meet the target of carbon neutral city. And these guidelines or strategies, they include also construction, because that is important in a city like Tampere, because it's growing all the time. But the idea is that all the new buildings will be net zero energy buildings, and the city is showing examples for the people living in the city and also for construction industries that this is what we want. And it's very ambitious for a city to take kind of a lead in the fight against global warming. Now the country target is that the emissions of the built environment and the construction industry will be reduced by 66% by 2035. So this is the state and the construction industry's common target as well. So the idea is to reduce carbon emissions by 66% by 2035, and then the total carbon neutrality is looked at 2050. And then the emissions will be reduced by 95% compared to the current level. This is also quite ambitious in my opinion, and there will be a lot of reach the target anyways. It looks like it's a long time, so 2050, but it's 28 years, 29 years goes quite rapidly if you think about it, on the basis of the history and the development earlier. And then how we analyze these things, earlier it used to be so that looking at the energy consumption, or energy demand actually, and the carbon emissions, it was a kind of a linear process from product manufacturing to demolition and recycle of the building at the end life. Then we had to include there the energy production for every step in the process. Typically, the buildings are looked at only as a building where the energy in the use of the building is a kind of a dominating issue. But actually, we have to look at it from raw materials to demolition and recycle as well, to be able to calculate the life cycle cost and also life cycle carbon footprint. And this is something that we at Sweco have been developing quite strongly for some years already, for 5-6 years now. So we have the tools to make the analysis for individual buildings, but then we can also analyze like town areas or neighborhoods or what we want to call them. And then there is also the circular economy that has to be taken into consideration, because this will then reduce in a way the emissions, because you are reusing all the parts of a building and as far as possible. But the problem is that if we have a building built in 1960s and you want to demolish it so that somebody can use the building and structures again, there's a lot of problems with the strength of the structures and also the building physical properties of the structures. And then again, there might be some problems with mold growth in the structures. So it's not very easy, but it's possible anyways. And this is also something that my colleagues at Sweco are looking at, how to kind of secure if the structures that you take out from a building that will be demolished. So in a circularity, I think that the new areas that we have to start rethinking things differently than we did before. Also, think that modular design might be something that helps in the circularity. So you can lift up the module in the building and lift it out if necessary. And the building should be in total to be designed for reuse and optimized life cycle as well. And then if something to be recycled is the bio-based materials. I think the recycling of concrete elements is not that difficult, but the only difficult part is that you have to be sure that it fulfills the requirements for human health, so that the already in use parts of a building don't contain like microbes that can be very difficult to get rid of from a building. And the microbe growth is also a health issue, a very strong one. And for the existing buildings, the idea is to prolong the life cycle, meaning that do the renovation and refurbishment, take into consideration the energy demands of the present day, and then reuse those parts that are not good anymore, and then recycle all other materials at the end of the life. There's an example whether we should demolish and build a new or refurbish and extend the life cycle of a building. Those graphs on the left-hand side, they are in Finnish, but the colored area means the construction volumes 1917 to 1989. And so that was very high construction boom during those decades. And on the right-hand side, you can see the area where this building is. It's a very low-rise apartment building, all concrete buildings that you can see in this video. And then we started to look at what should be done with these. So these bars here, A, B, C, A is the construction activities, B is the use, and C is the end life emissions. It's the total emissions. So if we demolish and build new, we are causing more emissions than if we refurbish and extend the life cycle of the building. And it's quite a lot, it's 20%, it's less. And at the same time, when we refurbish the building, we can improve the energy efficiency of the building so that it's on the same level as the new buildings or according to the present requirements for buildings and their energy efficiency. And also the material production will have some kind of a new good sides that we don't need new materials so much when we refurbish than when we are going to build totally a new one. And of course, in a refurbishment, you have to be able to use the existing load-bearing structures, so that because that if you have to change those, that will then be almost the same as totally a new build. So another example, we made a comparison between, not we, but the Housing Finance and Development Center of Finland. I remember that it was Sweco who did this analysis. So there were two similar buildings with the same architecture and same type of apartments in the buildings. One was one was designed as a concrete building and one was designed as a wooden building. There were a lot of similarities because all the underground structures like deck, garage, architecture, indoor spaces, windows, doors, heating, ventilation systems, and so on. Also, household equipment in the analysis was considered to be the same in both the buildings. And we estimated that the simulation would take 100 years. So the expected life cycle of a building here is 100 years. And then the analysis using the European norms. For the carbon footprint calculations, we use the Finnish tool one-click LCA, but also the LCA-EN system, which is commonly available in Europe. The one-click LCA is very handy because there is all the time renewing library of properties of different materials and different systems. So it's easy to use for a designer to make this kind of analysis. So we consider that the wooden building has, of course, a little bit lower carbon emissions, and the reduction for the wooden buildings, if we take into consideration all the materials and energy for 100 years, is 6%. And this is probably very low because the yard deck and the garage underneath the ground is the same for both buildings, and those have to be built not from wood, but typically they are built of concrete. But then if we look at only the materials, it's only 20%. So energy use is a very big issue here, and the emissions caused by energy production. But if you look at only the above ground materials, the wooden building gain 21% compared to concrete building. But it's also a fact that the housing areas are quite tight, and there is not enough space for above ground parking, and typically this kind of garage is a must, and you cannot build the garage underneath the ground by wood. So this is one of the examples. There are of course other studies done where the percentages are different, but probably it is clear to everybody that wood as a biomaterial, it has a lower emissions than concrete. But then again, there are buildings that cannot be built out of wood. There are buildings that can be built only with concrete. The emissions from concrete, this is a funny thing. I found this is from Unilever, which is a food product producer. And if you look at the emissions from concrete and cement, they are in the same level as potatoes or beer. But of course, the problem is that we are using concrete so massively, and that's why the emissions of construction are so high. I never heard that anybody or how many people it would require to drink beer as much as we use concrete in a building. So to kind of have even emissions. But then again, this pie here shows that 70% of all the emissions are other emissions which are not related to construction itself. And for building materials, it's only 6%. So, and concrete is inside of the 6%. Site operation, transportation is one thing also, and then consumption during the use of the building. So we are talking a lot about concrete and its emissions, but actually it's in the big picture, they are not so high. There are other things that are much higher than with the building materials. Then Mr. Kuittinen, who and a team made this kind of a report on how different carbon, let's say, capture systems might work. And it's important report because this Mr. Kuittinen is a senior advisor for the Ministry of the Environment in Finland, and so he is the one who is collecting the information that the ministry is using when they are making the new legislation for buildings. And here you can see that the approach, the 2.1 carbonation of cement-based materials is also one of the things to reduce CO2 from the air, and its applicability to construction is very high. So there are ways and means how we can, in a way, improve the image of concrete, which are not considered in the public discussion so much. Nevertheless, there's also cement manufacturers who have already now reduced the emissions from cement production by 50%. And that work is going on, I think, everywhere nowadays. They want to have kind of a greener concrete compared to what we have now. Then the BY here is a concrete association, but in Finnish the shorten is BY. And they are creating a low carbon classification, which is based on global warming potential of different concrete qualities. And this is then the greener the column is, the better it is, because the GWP 100 is what is going on now. And this is something that we have to improve, of course, to get the lower emissions. And the values for this table come from the European Product Declaration, which is mandatory for all products on the market. So they have been created or measured by institutions that have that are allowed to do it. These are anyways for the system, the low carbon classification, these are preliminary values and they will be verified, and this process is going on. Aalto University in Helsinki is doing this kind of work. But are these concrete qualities here, are they reachable? Are they already there, or is there still something to be developed? And the green ones here are those that probably at least a 50% of manufacturers can produce. And if you look at the red one, those are still out of reach mostly. But at some point, I think the industries develop their processes so that also the lower global warming potential concretes are available in the market, and it shouldn't take too much time. It's actually, question is on what kind of energy you're using in the cement manufacturing. If you can make the energy green, then you have also greener cement that you're producing. Of course, there are other emissions, but the energy use is the key issue. This is one of the systems that the concrete industry is developing to make the concrete more affordable and more interesting to all the builders, architects, and so on. Of course, it's very affordable now. It's very cheap, actually, but nevertheless, it has to be greener in the future, and this work is looking at that. And this is now a kind of a table of simple actions that can be done when you want to impact on carbon emissions, carbon footprint of a building. It's divided into different phases. And those kind of actions that this table is showing, they're quite simple, like material selection. You have to be careful when you are choosing materials for the building. Also choosing low carbon structures. And one of the things is that sometimes designers tend to over-dimension things so that you have too thick concrete layers or too thick structures where you could use less materials. And also you have to be able to optimize the building spaces so that you don't have too much extra and spaces that nobody is using. So if we look at then the circularity, waste reduction is of course the main issue that we should concentrate. The second is that we have to reduce what we are demolishing. and we can use those as material as well, and then energy production to get rid of the emissions from energy production. And then also consider what is the final disposal, what to do with the rest. To circulate the rubbish or do something else that is not causing any carbon emissions. But the use phase, of course, the energy efficiency is something that has to be looked at. And that's why in Europe, the requirements on a European level for the building energy efficiency are getting stricter and stricter all the time. And I think in Nordic countries, those are quite strict anyways. And that is happening on different sequences. The last time we changed the requirements was just 1 year ago, 2 years ago. And the next will be 2025. So slowly we make the requirements tighter and tighter, and the building industry has to be able to respond on these changes quite rapidly. So I read somewhere that David Fernandez was also a speaker one of the earlier sessions. I don't know if he has showed this system mirrors, which is requirements tree, how to analyze the requirements for the building so that you can see the outcome of the coming buildings. So this is a system where you put the certain issues like economic, environmental, social impacts, and then you give kind of indicators to each of those. For instance, economic, it's at the cost of time, environmental emissions, energy and materials, and the social size, safety, and third-party effect. And this is this kind of tools have been used earlier as well, but this is now exactly for concrete and to look at the total sustainability of concrete buildings. So it's not just the material, it's looking at all the buildings, all the issues related into the building. And this work has been doing in the FIB group 6.3 sustainability of structures with the precast elements, where I'm also participating in it, and my boss at Sweco is also participating. But this looks good to me because in environmental side, the emissions have the largest impact here. But the idea of the tool is that you can change those. These are not fixed, the percentages are not fixed, and you can change them. And that is, in my opinion, a little bit dangerous, because then you can use suitable percentage, not the real ones. And that might lead them to good results. And here is one of the examples. This is, if I remember right, Albert de la Fuente was giving a presentation in Malta in one of the conferences, and he's showing this. And here the emissions from concrete manufacturing are quite low. So I would disagree with these numbers. We know that concrete manufacturing up to now causes a lot of emissions, the cement manufacturing especially. So we should not give values that are under the reality. So we have to keep the system so that they are acceptable, so that nobody is looking at this is just greenwash, which might happen, of course, if you are using too good values in a system like this. And that was my presentation. Thank you.
Okay, thank you, Mr. Jyri, for the interesting presentation. So now we will enter the questions and answer sessions. So for those of you who wants to ask questions to Mr. Jyri, you can raise your hand, and then when I call upon your name, and then you can unmute yourself, then you can ask your questions. Or for those of you who prefer to write down your question in chat, you can also write down your question, and I will try to read or translate for Mr. Jyri. Okay, now we are Mr. Henry. Mr. Henry, you can ask your questions.
Mr. Nieminen, you are talking about zero energy building. As far as I understand from your presentation, it mostly concerns about how to utilize the heat from outside to be utilized for the internal usage. But as you know, Indonesia does not need heating. We are a tropical country and we need a lot of cooling. Do you have any insights about this zero energy building for such country like us?
Well, we did the analysis for a hospital to be built in India, which I believe is a hot country and very humid country as well. And there we didn't, of course, concentrate on heating, we concentrated on cooling. But the structures or the solutions that we proposed are in a way the same as we have in the cold countries. You have to insulate the building anyways to avoid heat transfer from outside to inside the building. You have to have, especially in hospitals, you have to have a ventilation system where you can also kind of extract the heat from the incoming air and use that, for instance, for warming hot water in the building. You have to choose the windows so that the direct sunlight coming through the windows is cut by the glazing systems. And you have to also have shading for most of the windows to avoid the overheating in the building. Basically, the thermal insulation is very important also in hot countries, hot areas, not as much maybe as in very cold countries, but it's there. And then also, I think the thermal mass in hot countries is more important than in cold countries. So concrete is a very good material for structures inside the building if you can control the overheating coming from the sunshine and outside the buildings. Basically, it's the same thing, but it's just turned around.
Okay, thank you, Mr. Jyri, for the answer. Is there any more questions from the audience? Okay, I have one question for you, Mr. Jyri. Okay. Look at your first slide, the building which you talk about in the top of the sea. So it should be it's susceptible to the corrosion issues. So I want to ask you for the strategy for the sustainability, the durability of the structure. Is it the same as the normal? I mean, the conventional cast-in-place concrete. Let's say we can use a higher strength concrete, or we can use a thicker concrete cover, or maybe we can also use the stainless steel. Is it for the precast concrete structure? We also have the same strategy for the corrosion protection.
The building, all the concrete parts except for the exterior layer that was contacting the sea, they were waterproofed. And there's 3 layers of high quality waterproofing that prevents the seawater to go into so deep into the structure that it would have an impact on the steel and the concrete elements.
Oh.
So there was something that was also the building authorities in Helsinki were a little bit concerned about this, but we found out a way how to do it. I wasn't the designer in the building. My position was that I was so-called moisture control coordinator, so who is responsible to check all the drawings, design drawings, and also check that the building will be built according to the drawings. And I found it very interesting that the system that was built, they said that it's not really expensive. It's just that you have to do it, and you find out ways and means how to do it efficiently, but also affordably. So the building itself is, of course, a very expensive building, and the flats, if you want to buy one, the prices are up the sky. But nevertheless, it was, I think it was very well considered issue, and there was the structural designer for this project, and we had a lot of discussion, especially on this issue that how can we be sure that the seawater stays outside the building. But it was finalized last spring, so far at least half a year. It's okay, but the design life is of course 50 years from now.
And during construction for the connection, is there any special treatment for the connection? I mean, the connecting elements?
No, in my understanding, there's no special treatment, because all those areas in the building that can be, if the seawater level is rising, the waterproofing goes so far up that the seawater cannot impact on the building parts inside the waterproof.
Okay. So one more question. I'm interested, and it's a bit technical. So the 3 layers of waterproofing, how thick is them? How the thickness of the waterproofing?
Waterproofing, it's well, there's a classification for waterproofings used in the building, but I don't know, remember what is the class, but it's 3 layers of high quality bitumen waterproofings, and those are glued to it, so that the bottom layer is fixed mechanically, and 2 others are just glued. And then it's pressed by the concrete so that it's in a very tight area. So I think it's quite well also secured that there will be no damage into the waterproofing.
Okay, so the concrete itself is a normal strength. I mean, the concrete.
I don't remember. I really don't remember what was the strength of the concrete that is underneath the sea level. But there was a discussion with the building authorities, and I remember that they accepted it. So I don't remember now the class. Design was done some 4 years ago, so a lot has happened after that.
Okay, thank you for the answer. Is there any question? Okay, yes, Professor Antoni.
Yes, I have a question about the sustainability and durability. I mean, from your presentation, we have been shown that the sustainability aspect of the building, and I think for your case, is the especially the precast building has been considered. You shown us like the roadmap to achieve the sustainability of the building. And in what is your stage in the application of that the roadmap to achieve the sustainability? And as for the durability of the building, I mean, is there any like special treatment or what you use to ensure that the building have a good durability? And is it just like all in the standard and then you just follow it? Is there any different with the common concrete or steel building on it?
No, the solutions are the same. It doesn't. Well, in our climate, of course, the thermal insulation and the ventilation heat recovery are the most important issues. But the requirements are the same for all buildings. And I have been working with this so-called low energy, zero energy buildings from the beginning of my career at VTT, and we have a number of examples I think the first zero energy building was built already in 1993 or something like that. And after that, we had the contacts with the building owner time to time and discussed about how it's going. And he said that there's no problem with this building. It's like living in a normal building. The only difference is that the building uses so little energy. So and then of course our building requirements, they have been changed, of course, when we are going towards the low carbon build construction. They are getting tighter and tighter. We had to change in 2017 or 18, and the next one will be 2025. And it will mean that the new buildings have to be even more energy efficient than the new buildings now. So there is a roadmap for how to make the carbon neutrality to happen in Finland. But then again, of course, it will take time and it will take resources as well. The construction will be more expensive in the future than it is now. But then again, the building industry is developing new solutions that might then also help with the cost issue. So it's a kind of zero-sum game that is going on. If you increase somewhere, you have to reduce somewhere else.
Mm-hmm.
But I think we are on the good way to the final target.
Mm-hmm. As for the design for the precast building, like what is the normal life cycle that you considered in Finland?
Typically, it's 50 years, but I know that the building owners demand higher surface life as well, 100 years.
100 years, no?
But it's not an issue in the design. We have to fulfill the requirements set by the law. But if the building owner wants to have something else, we have to fulfill also those requirements. So it's a thing that, let's say 25, 30 years ago, it would be impossible. But the attitudes have changed so much towards the carbon neutrality that it's easier now.
Mm-hmm.
And the change was actually very rapid when it started. Because the industry see business over there as well. Who is the first, he will gain much more than the others.
I have one more question, like that is a personal interest for me, because like I see that the trend is changing on the concrete and steel building to become a wood building. Is it also occur in your country, Finland? What do you think about the future of the precast? Can it use like other building material also, and what is the relation with the engineering wood?
This is true that the wooden buildings are getting more and more popular, but the problem is this in Finland, but also in Sweden, I believe, that we have also the pulp industry making paper, and they need more material. So there's a competition on who is getting the best wood. Constructors, they want to have, of course, the very good wood, and the pulp industry don't need very high quality wood. But we have a limited resources, the forest resources, and there will be the thing that if our pulp industry is growing like it's been growing, then we will have, we don't have enough trees to cover it. And large areas of Finland have been protected by law. You cannot touch those areas, which is a good thing because we want to have the forests. So that is also an interesting thing, because I believe that in the future, when we can reduce the emissions from cement production, the popularity of concrete buildings will start rising again, because it's strong. There is no mold growth on concrete. It doesn't rot. And it's not sensitive to water, unlike the biological materials are. Because one of the big issues in Nordic countries is that there will be microbe growth in structures where you have a lot of biomaterials, and that is a health issue as well. Of course, that can happen also in concrete structures, but less than in wooden structures. But I believe that people like wooden buildings. I live in a wooden building that was built in 1954, and it's in a good shape, no problems at all. But just changes. New materials are coming, new systems are coming, and then slowly we are also trying to reduce the amount of wood that is needed for the building, because it's a cost issue as well. So wooden buildings will be built out of prefabricated elements, as also the concrete buildings mostly are. And the idea of these prefabricated wooden elements is that we don't use as much wood there than we used to do earlier.
Okay, thank you, Mr. Jyri, for the answer. So now, Mr. Henry, you raise your hand, please.
Mr. Nieminen, talking about durability of precast element, precast building, in general, can you give us some guidelines about the comparison between this precast building durability against the conventional method of constructing a building? Of course, always using cement, concrete.
Yeah, I don't see any difference there, because it's a different story to build the building out of precast elements than from side cast walls and floors. It's a matter of opinion whether you want to build it rapidly, which is with the precast elements, or if you have time to let the concrete dry out before you go on. So I don't think that there is much difference in costs either. So, or if there is, it's not so large. Some builders like more side cast concrete, and some builders like more on precast. But I'm not a specialist here, so I'm the sustainability guy.
Okay, thank you very much, Mr. Nieminen.
Thank you.
Okay, thank you, Mr. Nieminen, for the answer. Is there any more questions from the audience? Maybe some questions from the students. Okay, maybe if there is no more questions, I would like to say thank you for Mr. Jyri Nieminen for sharing your knowledge and experience with us. I believe it will be useful for our life here. Thank you.
Yeah, thank you. It was interesting to be here.
So yes, thank you, Mr. Nieminen. Yeah, how should we proceed? We still have some time. Gimana Pak Jimmy? Istirahat dulu atau lanjut?
We'll have a 10 minutes break or
Yeah, 10
for the
minutes.
next session.
So
now it's 2 o'clock, so we will come back at 10 past 2 o'clock.
yes. So yes, once again, thank you, Mr. Nieminen. And then you can stick around if you want, but you can also leave if you have other things to do. So we'll proceed for the 10-minute break, and then we'll return for the second session. Thank you so much, everyone.